All right, today we're jumping into a really fascinating scientific paper that explores a pretty wild idea. We're looking at something called the Super Bloc experiment, which asks a really fundamental question about water itself. So here's the core question they're trying to answer. Can an object actually change the physical and chemical properties of water just by being near it, with no physical contact at all? I know, it sounds a little like science fiction, but a team of researchers set up a really rigorous experiment to see if it was true. And here are the stars of our show. See these two boxes? They look exactly the same, right? Well, one of them is the Super Bloc, a device that supposedly emits some kind of special, subtle signal. The other one, it's a decoy, a total fake that does absolutely nothing. The entire experiment boils down to comparing what happens to water placed in the real one versus the sham one.
Okay, so before we get to the results, you're probably wondering, how could this even work? What's the theory here? Well, the researchers are tapping into a pretty controversial idea in biophysics, sometimes called water memory.
The first big idea is something the authors of the paper call a subtle field. Now, let's be clear, you're not going to find this term in a standard physics textbook. It's what the researchers are using to describe a hypothetical, super weak signal that they believe the Super Bloc is emitting, something that our usual equipment can't easily pick up. So if this subtle field is the message, what's the receiver? The theory suggests it's something called coherent domains. The easiest way to think about this is like tiny organized neighborhoods of water molecules that form inside the otherwise chaotic liquid. The idea is that these little domains can actually pick up, store, and even pass on information from these weak signals, changing the overall structure of the water. Now, when you're making a claim this extraordinary, you need some seriously extraordinary evidence. And that brings us to the most critical part of this study, how they actually designed it. The researchers knew they had to get rid of any chance for bias, so they set up a very strict, double-blind experiment. So here was the game plan. First, they made up a bunch of different water solutions, some acidic, some alkaline. Second, they put these samples inside both the real Super Bloc and the fake one. Third, and this is the absolute key, they blinded the whole thing. The samples were just labeled A and B at random, so the scientists doing the measuring had no clue which was which. And finally, they measured everything they could think of. pH, conductivity, you name it. And here's a peek at what that actually looked like. You can see the bottles of water sitting inside one of the devices, just getting exposed to, well, whatever signal it was or wasn't emitting. And the researchers themselves really hammered this point home. The code, the one that revealed which samples were the real deal and which were the controls, it wasn't broken until after every single measurement was taken and all the stats were run. This is so important for preventing bias, even the unconscious kind, from creeping in. Okay, so the setup was legit. The protocol was tight. They collected all their data. So, the million-dollar question, when they finally cracked the code and unblinded the results, did they actually find any difference between the water from the real device and the water from the fake one? And this is where things start to get really interesting. When they looked at pH, the results were split. For the acidic water on the left, not much happened, no real difference. But look at the alkaline water on the right. The water exposed to the Super Bloc actually became a little more neutral. The change was tiny, but it was statistically significant. That little p-value there means there's less than a 3% chance a result like this would happen just by random luck. All right, next up, something called oxidation reduction potential, or ORP. You can think of it as a measure of the electrical tension in the water. And here, the effect was even more dramatic. Across the board, they saw a clear, statistically significant jump in ORP. And check out that p-value, 0.004. That means it's highly unlikely this result was just a fluke. But it wasn't like everything changed. When they measured electrical conductivity, they found nothing. Zilch. The water from the real device conducted electricity no differently than the water from the fake one. This is actually a really important detail because it shows that whatever this signal might be, it was being very selective about what it affected. And then there's the UV light absorption results, which might be the weirdest one of all. Here, the effect completely flipped depending on the water's pH. In the acidic water, UV absorption actually went down, but in the alkaline water, it went up. Two totally opposite effects coming from the same device. So you're probably starting to see a pattern emerge from the data, right? It seems like the alkaline water was way more sensitive to whatever was going on. That's where all the most significant results were popping up. So naturally, the researchers decided to zoom in on that. And boom, here it is. This is what the paper presents as its strongest piece of evidence. Looking specifically at alkaline water with a pH of 8, the increase in UVB light absorption was highly significant, and there's that same tiny p-value again, 0.004. According to their data, this was the most powerful and most reproducible effect they saw in the entire experiment.
So let's pull all of these different threads together. We've got some properties that changed, some that didn't, and some that changed in opposite ways. What did the authors actually conclude from all this? Okay, so to recap the key findings, they saw a real effect on pH, but mostly just in the alkaline water. They found a clear increase in the water's electrical tension, or ORP. At the same time, electrical conductivity didn't change at all. And finally, they saw that strange opposite effect on UV light absorption depending on the pH. It's a very specific fingerprint of changes. So based on all these results, the authors make their final claim. They state that this double-blind experiment provides real empirical evidence that the Super Bloc device is, in fact, producing some kind of reproducible signal that is capable of influencing water systems. And that leaves us with a truly mind-bending question. Now, this paper makes a claim that flies in the face of a lot of conventional chemistry. But if we just take its findings at face value for a moment, if it's true, if the actual structure of water can be altered by invisible fields, what could that possibly mean for biology? Where every single process of life happens inside water. It's a question that really challenges our basic understanding of how the world works.